Our next Tech Talk will be presented by Professor Ninghui Li. Ninghui is a professor in the computer science department here at Purdue and a long-time CERIAS affiliated faculty member. Over his career here at Purdue, Ninghui has worked in several areas and has been exceptional in each of those areas. And one of the many reasons why we've asked him to speak today, not only we think his research is of great interest, but he's excellent at communicating his ideas to even non-technical people like myself. So an awful lot of people that have seen him present his work have been able to very quickly digest and say, you know, I think we could put this in play here. And we're hoping that since there's a very diverse group in the audience today, that there is probably many applications for this particular project that we've asked him to highlight. So, Ninghui, thank you.
Hello? Okay. Yeah, so I guess the first time I attended the CERIAS Symposium was also just before joining Purdue, so I accepted Purdue's offer and came here to visit. That was in early April, and I remember it was cold for a few days, just like this year. That was 2003. And so today I want to talk about firewall policy language and complexity. This is joint work with my PhD student, Hai-Ning Chen, my postdoc, Omar, we are in Department of Computer Science, and also Professor Robert Proctor, and his PhD student, Jing Chen, in the Department of Psychological Sciences. And then Warut is a graduate student in Granite, and before he started as a graduate student, he worked as a system admin and actually configured many firewall policy before, so he made a contribution to this project. And also, we collaborate with researchers at IBM T.J. Watson Research Center. So Suresh, Ian, and Yungja, and Ian is actually here. So we started this project because of funding from the National Security Agency. Have this Science of Security Lablet funding program where they want to establish community of researchers and fund the research that look into the science of security instead of just fixing urgent problems. And we got the project funded through North Carolina State University, which have this, one of the university have this Lablet program. And this particular project, we propose to develop metrics for policy complexity because access control policies are used in many places. So this talk will focus on firewall, but there are also, I guess, database have access control policy. When I say it's security enhanced Linux has fairly complicated policies that I think one of the reasons that make it maybe not as widely used as it could have been is because it's very difficult to configure and understand the policy. So we want to understand, can we measure policy complexity? Because one of the important, I guess, scientific aspect is being able to measure things. Now the question is, how do we define, what is the thing we want to measure? How do we define policy complexity? To us, it seems it's really a complexity regarding the interaction with humans. It's not really so much how long it takes for a computer to process some things. So that's not what we are most interested in. What we want to understand is, can people understand this policy? Can people make modification to the policy in a correct way? Can they write policies that actually achieve what they intend? So then the complexity must be defined as how easy humans can understand and update the policy, can write things to achieve their perspective. Now the question is, well, how do we evaluate this? How do we measure it? Is it even possible? So one sort of first step is we can take the policy, turn it into some standard representation, and then measure some quantity. For example, I guess the best field where we draw analogy from is programming. So how do we measure complexity of software? So very crude measurement is a line of code. It's not good, but at least you're measuring something. And then there are other sort of a number of other proposals for software complexity. So basically, but they are marrying something. Now, so then we have to convert policy into some canonical form. Now, what is this canonical form? And then we realize sometimes when you write the policy in one way, it may become very difficult to understand. And when you write a policy in a different way, it may become easier to understand. Now, so this how to present policy become a central issue. So before we can answer quantitative measure, we have to think about representation. So then how do we do it? So in order to do it in a way that makes sense, I think we must start from something concrete. We can't just sit down and dream about access control policies, because we really want to measure things that, that matter in the real world. So then one place where there are real policies is firewalls, right? So I believe most of you in the audience should be familiar with firewall, but this just give a very brief overview. So a firewall sit in between network and maybe the outside internet, and then try to determine whether a packet is allowed to go through according to some firewall policy, and therefore it can protect against certain kind of attacks. So when the packet comes along, the firewall will try to match it with each of the rules in the policy, and the first one that match this packet will be will decide whether the policy should be accepted or discarded. So in this particular example, the first rule that matches it is this number 4. So all the source IP, destination IP, and the port all match. Then this rule is applied, then this packet is dropped. So here we use star to represent it matches everything. So I don't know. So maybe I want to do a poll. So how many of you have configured firewall policies before? Oh wow. That's I guess very high percentage. I guess that's speak to the kind of audience we have. So so firewall policy have followed this first applicable semantic. So there may be multiple rules matching any single packet, and they may have different decisions. Some rule may say accept, some rule may say deny or allow or deny. So the semantic is the first rule that matches will decide. And this means that a rule will interact with other rules that may overlap with the range of packet that this apply. So if you want to insert a rule somewhere in the policy, this may impact rules come before and after it. So it's really difficult to infer what exactly happens when you insert one rule into the policy. And also some firewall policies can be very large. So I've seen articles saying there's like a policy with thousands of rules or hundreds of rules. So we've seen many policies with hundreds of rules. And this can be very complex. And what makes it more challenge is firewall policy oftentimes is not a fixed object. So it's not like you specify and you're done. So your business changes, you may have new software running, and there's new attack being discovered. All of them require updating the policy. So then the question, well, how can, so is this something that easy to do? Or is this a current situation with sort of the current technology we have satisfactory? And I think most people will agree with me that the answer is no. And there are researchers have shown that firewall policies tend to be error prone. So they identify sort of, so one researcher identified 36 different categories of things that they think shouldn't happen. And then they analyzed, I think, several dozens of actual firewall policies and find that those policies exhibit these errors. And they also find that the number of errors positively correlate with the size of policy. And I argue that what they found are not necessarily all of them errors. So there are some of the things maybe not desirable in general, but maybe there's reason for one organization to do that. But of course, many policy errors are not found because sometimes you're just not specifying the way you want it to be, but they won't fall into any of the global 36 template of things that could go wrong. I think one of the problem is the current firewall policy language is too low level. So I've seen people comparing programming, writing firewall policy to programming in assembly. I think there's some truth to that, even though I would say it's more like programming in C, but without functions. You're not allowed to use function, but you can use goto as many as you want. So you basically have a huge chunk of code all in the main function, and you can jump back and forth. So I think that's similar to what we have today with firewall policies. So so I think the root cause of the policy errors in firewall in firewall policies, this is obviously one of the reasons. Is the conflict, because this introduces interaction between different rules. But I think this really more than that. I think a very important aspect is the size. So if I have a 10-rule firewall policy, no matter how many interactions there are, I can manage them. I can understand them well. But when I have hundreds of rules, even if there's no conflict, I've seen policies with over 600 of rules, and all of them are except the last one is denied. But still, it's very difficult to actually understand what that policy does. Or if you want to have a high-level overall understanding of what the policy does and whether it matches whatever the admin have in mind, it will be difficult. It will be, very difficult, if not impossible. I think but size is something we cannot change, right? We cannot say you're not allowed to write a policy of big size, because your natural goal, maybe the policy is complicated when you have many machines and different requirements. I think the main problem is firewall policies do not provide any abstraction to allow you to understand things in a hierarchical fashion. So right now, everything is flat. If you want to understand the policy, you read all of them and understand all of them in a bound. And as we all know, at least intuitively, this is difficult. So the way people deal with size, large size, is to break them down. So you have abstraction so that, for example, when you have a big program, you can first roughly understand what each function does and see how they make sense together. And then, when necessary, you delve into the detail of each function and understand one of them. You understand each of the data structure independently. So there has to be some abstraction to allow us to not understand everything in one chunk. We can understand them piece by piece and together still form a global picture. And this is what's not available in today's firewall language. So to deal with this firewall policies, there are a lot of related work. So most of them are sort of fall into this category. They provide tools that enable you to analyze firewall policy. A lot of them detect anomalies such as some rules are shadowed by others, so they are useless. So that may indicate error. And some of them enable you to query a firewall. So you can issue a query saying, well, what kind of packet will be able to reach this? And then you get the result. You can see whether that match what you have in mind. So in my view, all of these tools are useful, but they are basically like debugging tools or static analysis tools for developing software programs. So they are helpful, but they can't compensate for the fact that you are using a very low-level language. So if you are writing program in assembly, while you can develop the best debug tools out there, it's much better to actually move out of assembly and write your program in a modern modular programming. Modern programming language support modular programs. So then there are some works that look at improving the syntax of firewall languages or make them somewhat higher level. But I argue they don't provide a real abstraction. What they provide are some syntactic sugar. So instead of seeing all this this very low-level syntax, you see something that's closer to text. Or they provide macros. So you can define, say, these subnets include these addresses, and then you use the subnet's name in the policy. Then this will apply to all the hosts in that particular group of network addresses. So they are helpful, but they are just macros. They don't provide real abstraction to allow this hierarchical understanding of a policy. So then, before we try to really make progress towards scientific understanding of policy complexity, so we started trying to design a language to enable better specification of firewall policy. So, and our inspiration are basically taken from programming language domain, which have really, I think programming have changed a lot over the last, I guess, 4 to 5 decades. But I think at the fundamental level, firewall policy language didn't really change. But even though it has, I guess, a shorter history than programming. So we want a policy language that enable modular policies. And our proposal, this is sort of our first proposal, is what we call TMFL, which stands for Tri-Modular Firewall Language. It's called tri-modular because in our language, a policy is organized into 3 kinds of modules. So a policy will have these modules one after another. They are a primary module, auxiliary module, and template module, and we're going to see what they really mean. And one important part that enable modularized policy is we require the policy author to choose one of source or destination IP as the primary address. And this will be used to group policy into modules. And based on our analysis of about a few dozen real-world policies, most of the time the destination IP is a better choice. So in this talk, the examples will use destination IP as the primary address. So what are the 3 modules? A primary module consists of rules that have the primary address field being some concrete value instead of the star for all. So in this example, the destination IP is primary address. So this represents a primary module defining policies for this subnet, 139.68.171.star. And it is required that all rules in this module must have destination IP within this range. And furthermore, any 2 primary module must cover entirely disjoint ranges. So if I have this one primary module for this subnet, then no other primary module can have rules with destination IP within this subnet. So this enables one way to sort of separate policy into different primary modules so that if you want to understand the behavior for one destination subnet, you only need to look at the relevant primary module. You can ignore all the other primary modules. And in our syntax, we add additional field label, which is used to tell these 3 rules actually belong to the same primary module. So that's a primary module. But of course, not all rules have destination IP being concrete value. Some of them will have the destination IP being this star. So they are globally applicable to all destination IP addresses. So those rules we call auxiliary rules, and they form auxiliary modules. And auxiliary modules are grouped based on the type of rules. So for example, these rules are the same type because they have specific value in the source IP, and all the other values they have this don't care or star. So intuitively, this kind of rules here means that they want to blacklist certain source IP. They're saying anything coming from this source IP, I don't want to allow. So we group these auxiliary rules into auxiliary modules based on their type. So each auxiliary module consists of rules of the same type. So another example auxiliary module is here. So these rules will block certain ports. So they don't care the addresses, they'll just block this port. Yes. So these are auxiliary modules. And then finally, from analyzing the real policies, we realize sometimes you have a sequence of rules that are used again and again on different destination IP, on different primary address fields. So then those can be distilled into a template, and then this template can be applied to each of the different destination IP. So this policy that I'm referring to has I think has 209 rules regarding the TCP traffic, and it's used in a real organization, and we have contact with the actual system admin. So therefore, we can verify some of our findings with them. So that's why I use this as an example. So in this policy, we find this template consists of 7 rules, are used more than 20 times, applied to different subnet and different hosts. So yeah, so then these templates can be instantiated in the policy. So here are examples where we instantiate the template. So this rule just instantiate this template to this range of IP addresses, and these next couple of rules is another primary module that are applicable to basically this IP address. And you can see this IP address we apply this template to this IP address, but there's also a bunch of other rules that are applied to this IP address. So these together form the primary module regarding this destination IP. Okay? So the semantics of our language is actually very easy to define. We define it by giving a transformation from our policy to standard firewall rule set. And it's very easy. Basically, for every instantiation, something here, we are using this particular template module here. We take the 7 rules and then plug them here and replace the destination IP with the value here. And once you do that, you remove the labels, you remove the template definition, you get a standard firewall rule set. And that's the sort of the meaning of our policy is defined by that rule set. Now, what are the advantages of using this approach? Well, the first obvious one is you can hope you may be able to reduce the number of rules. For example, in our example policy, which have 209 policy, we're able to reduce the number of rules to 68 because there's this 7-rule template that are applied over 20 times. But I think this is really it's not the most important sort of benefit in my view, but it's something quantitative and easy to see. Another benefit is this approach enables policy refactoring, just like code refactoring. So in at least 2 senses. So the first one is when you see a sequence of rules that are used again and again, then you can create a template and then you apply them. So this is one sort of refactoring, creating functions from your code that are reused. Another kind of refactoring is when you have a primary module and it becomes bigger and bigger, then it becomes difficult to understand what happens in that primary module. Then you can split that primary module by dividing the range of destination IP into 2 disjoint range, and then each of the primary module will become smaller. So you can do that kind of a refactoring to avoid overly complicated primary modules. So that's another benefit. Also, from policies we obtained, we find that many policies have this stealthy rule near the top of the firewall, which says for the machine running the firewall, only particular connection can go in. Everything else is blocked. So that is something that's easily, actually somewhat motivated the design of the primary modules. You specify all the things together so that you can easily see for this destination IP, this is what can happen, and everything else is blocked. And the requirement that different primary modules cover disjoint things enable piece-by-piece understanding of the policy. So to understand what happened in one subnet, you only understand the relevant primary module and all the other auxiliary modules that may interact with it, but you don't need to look at any of the other primary module. And finally, because we provide this module and this primary address abstraction, they enable a way to come up with a global understanding of a policy. And this is, I guess, difficult to read, but this is the summary of the 209 rule policy that we are able to come up with after converting it into the trimodular. So in the beginning, there's a list of source IP that are blacklisted. And then this template is applied to 20 plus different IP addresses and subnets. And this module itself, we've seen these 7 rules. It allows some specific traffic from specific IPs, and then otherwise block traffic to this port. And there are 2 hosts that are apparently mail servers because they apply this template module, but they also have port 25 open to 2 other specific hosts. And then there's this host has additional port open beyond this module. And there's this host is most special. Beyond the module, it also have a bunch of other rules allowing certain traffic. And then after this, we have another auxiliary module which blocks all these ports. So anything not already allowed regarding this port are blocked. And finally, everything from a certain subnet is allowed, and everything else is blocked. So I think this enables a global understanding of what the policy does. And then you can, for someone, if you want to understand, you can go into detail to see, look at the individual IP addresses to see whether they really did what you wanted to do. And I would argue, I would claim this is very difficult, if not impossible, to distill something like this from the original policy. So finally, a very important side benefit is using this make policy, we argue that using this make errors in policy easy to discover. So in fact, we find that just by converting the policies into our module, actually the conversion, most of the conversion is done manually. It's by I load the policy into a spreadsheet, and then I try to move rules around while making sure that I'm not changing semantics, and organize them into what I wanted. And sometimes I will see, hey, this moving cannot be done because of this. And sometimes just by moving this and try to make sense of it, I find things, this looks strange. This shouldn't be things like that. So the next couple of slides show some example errors that we have discovered that have been confirmed by the admins. So the first, there are a number of redundancies. So these are, but these, I don't claim these are sort of special of our approach, because there are any number of approaches that can discover policy redundancy. But the rest of them, I think it's, I haven't really seen papers discussing this kind of policy error discovery. So one error is inferred from rules like this. I call them sort of consistency attitudes towards certain services. In this case, it's UDP 161. So anyone can see a problem with this set of rules? So it's sort of we're sort of making guesses, right? Making guesses of the intentions. We're not. So the kind of error we have, we're not sure they're error, but fortunately in this case they are verified. And there are actually more rules like this. There's lots of rules that says for this port, for this destination port, we only allow certain specific source, and everything else is blocked, right? So and this kind of pattern repeats multiple times. So the intuition is this port is really sensitive, right? Even for this host that I want them to receive this port, only certain sources are allowed. Everything else is blocked. However, for any other host, this is wide open. So this port, any address can send it to any host. So in a sense, this is sort of a trust inconsistency. At some place, you can infer that certain port is considered quite sensitive. I want a very strict control of them. But then you realize in other places, this implies this port is not sensitive at all. So, and also there are a sequence of this. Some of them actually just miss one of the discard rules. There are maybe like 8 or 9 of this kind of hosts that can receive UDP traffic. And also we realize there are inconsistent application of the 7-rule template. So this 7-rule template is applied over 20 times, but one time the hosts only have 5 of them instead of all 7. So then it turns out that that host is sort of no longer there, but the policy was not fully updated to reflect that. And finally, even just look at this policy, there's actually something inconsistent. So anyone see what the... Yeah, so you saw it? No, so these are allow come earlier, so they allow things from specific source. But so this basically says for those port, only things from this port is okay, but otherwise I deny it. So that's the intention. Yeah. So actually I didn't notice this while I first find a chunk of a list of errors and send it off. And then after a few days, I look at this template and think, this looks a little bit strange. So what looks strange is the fact that, so the pattern is we allow this port from specific source, right? And then we deny it otherwise. But here we allow things to the 2 ports, but we only deny it to 1950. We didn't deny 1951. So so either you don't need 1951 here because then this will be allowed sort of by default, or so it's just something doesn't totally make sense. And Actually, because this one is late, I'm not absolutely sure this is an error, so I need to double check. But I strongly believe the intention is to have this 19. Because if you look at the original policy, these rules are all dispersed. The original policy is sorted based on source IP. So you wouldn't be able to see this because all these rules are in different places in the policy. Okay, so so we have this language, and we also propose a process to convert existing policy into this language. And this is what you do. So first, you need to choose whether to use source IP or destination IP as the primary address. And the basic guideline is we want fewer rules with the star in the primary address field, because we want to having lots of primary modules are not as hurtful as to understanding as having lots of auxiliary module, because primary module do not interact with each other. Auxiliary module have global effect. So that's the guideline for choosing this. And then after that, we can identify and remove redundant rules. So there's standard algorithm for doing that. And then you want to reorder the rules so that auxiliary rules are merged together so that they form a bigger chunk so that you can mentally analyze, say, this chunk is blocking source IP. This chunk is blocking certain port. This chunk is doing something. So you can, so that there's fewer chunks for you to mentally sort of understand. And then you need to reorder the rules to try to create this primary module so that rules are about the same destination IP addresses should be merged together, so physically adjacent, so that you can create modules from them. And then finally, if there are patterns, we can create templates, and then you can create primary modules. So my student Haining developed a tool that sort of help automate this process. So before the tool, as I said, I was basically doing it using Excel. The tool help automate some of the steps and also do error checking. So if you're moving something, but it turns out that move that will change the semantics, then the tool will stop you from doing that. The tool is not quite mature yet, and also I think I'm running out of time, so I won't show the tool. So the next step, well, does this help leading to the original vision of a metric for policy complexity? I think it helped a little bit, but I'm getting somewhat, I guess, not as optimistic regarding the ability to coming up with really good policy complexity metric. Again, I don't think there's that well accepted metric for program complexity. So there are some that are used, but they are not sort of people consider them really a golden measure of program complexity. So if it's not possible to do it for program, we probably won't be able to do it for policies. But I think we can have at least some metric that have some use, just like in the software engineering field. And we are developing a user study to verify that policy in our language indeed are easier to understand. And we are thinking of how to design study to verify it's easy to write and update policy in our language than the standard language. And also, we want to develop method to automatically discover policy errors based on the sort of the experience we have. And I really, so all of this work depends on access to real-world policies, and especially real-world policies that are live, that we can ask someone if we discover this, is this really an error, or is something just you really intended? So if some of you have access to that, I would be really, really happy to collaborate with you. Okay, thank you for your attention. I don't know whether. Thank you.